for 3 months in 1999 to 2000 with support from National Board for Higher Mathematics and the short-term visitors grant. Professor Cutcosky has more than 100 publications. He has guided or is guiding about 15 students for PhD. He had organized several conferences and also he has given lectures in more than 275 places or 275 times. So we are very happy that he is here with us, and his lecture will be related to Abyankar's first work, PhD work, on resolution of singularities for characteristic P. So now I request Professor Cutcosky to start his talk.
Thank you very much for that introduction, and I'm really very happy to be here to honor Professor Abhyankar on this occasion. In my talk here, I'm going to tell you about what the state of the art is in resolution of singularities and positive characteristic, and we will see that that's really not very much more than what Abyankar had discovered when he laid down his pen on this subject some years ago. Okay, so I'm going to start by giving some concepts about this. So some notation. I will take a local ring. I'll write MR for the maximal ideal. Oh, it doesn't work. It just blinks. K equals R mod MR is a residue field. And it was Zariski who determined what the correct definition of a singularity was, or a lack of singularity. So R is a regular local ring if the dimension of M mod MR squared is equal to dimension of R. At the time, this was somewhat controversial for various reasons. It's still there are some people that resist this definition, and in a moment, in case you don't know this, I'll mention what the alternate definition is. Okay, so what I'm going to do is restrict to the to make things easy, if you will, restrict to the case of an algebraic function field over an algebraically closed field. So what is this? This just means a finitely generated extension field. So you have a dimension attached to that. Every algebraic function field has a expression like this, where this is a rational function field. Yeah, D variables. Okay, and this D is well defined whenever you have this representation. Okay, so a notation which Abyankar used, which is I find very useful in this subject, is the concept of an algebraic local ring of a field. So this is a subring of K, which is a localization of a finitely generated K algebra, and has the same quotient field as K. Okay, so to make things a little more straightforward, that we will generally assume that that is the residue field. Okay, and I guess we do things right, we can generally reduce to this case. Okay, well, in this case, since K is algebraically closed, we can use the classical definition of what a algebraic local, about what non-singularity is. So you will have a representation then in fact, I guess this isn't an example. I can just call it this. We can always write it like that, where M is equal to a maximal ideal. In fact, P is a prime ideal in a polynomial ring. K adjoin x1 out to xn. And M is a maximal ideal. So since my ground field is algebraically closed, this has this nice expression like this. This is the Hilbert's Nullstellensatz. And I'll take this vector here. A bar is equal to A1 is something in K to the N. Okay, now we've said that the dimension of R is D. D is dimension of R in this case. That's the dimension of the function field. And in fact, the Jacobian criterion tells that R is a regular local ring if and only if the rank of del Fi, a del Xj of A bar is equal to N minus D. So this is the old definition of non-singularity, but the implies directions may fail if K is not algebraically closed. Okay, so that's why one has to have this other more exotic definition. Okay, so this is the Jacobian criterion, which for our purposes, since K is algebraically closed, we can use. Okay, now...
excuse me?
What?
FIs are the generators. I guess FIs are the generators of P, right?
Yeah, it looks like I didn't write that, did I? Yeah, so this should be written here, fits in here, F1.
Any set of generators, right? Or you
yes.
want to take
Maybe I want this to be the M here, I think, right? That should be like that. So it doesn't matter, of course. I think that's right. Okay. Okay, so now the question is about what is an algebraic variety, and this is something that's never been completely settled. That I think this business about the algebra, the local rings, and so on, that's pretty established ever since I guess the notion of a ring came about. But exactly how you put all these things together into objects, what geometric objects are and how you describe them is a little uncertain. But what I like best, I think, is the method which Chevalier introduced, and certainly Zariski developed, which is that in algebraic variety X, and then this is where it starts getting difficult, I'll say, is a suitable collection of local rings in an algebraic function field. K is equal to, usually you write something like K of X. Okay, so that's that you need some, if you want to describe other structure, you need some some more things, but basically that's the idea. And a lot of things can be answered just by looking at it this way. Okay, so what does it mean for X to be non-singular? If all local rings of X are regular local rings. Okay, and that will happen if all the local rings of the actual physical points, the closed points, are regular local rings, the d-dimensional local rings. Okay, so what Zariski did, well, in fact, actually, to some extent, this was anticipated before this, but I think really creating the idea of using general valuation theory as a method of approaching algebraic geometry is due to Zariski. Okay, so evaluation nu of K is a map nu from K minus 0, the multiplicative group of the field, onto a totally ordered abelian group, where nu of Fg is nu of F plus nu of G. Nu of Fg, nu of F plus G, is greater than equal to the minimum of nu of F, nu of G, and nu of C is equal to 0. Let C an element of K star, the non-zero elements of the ground field K. Okay, so of course this third condition isn't part of the definition of evaluation, but to be evaluation of algebraic function field, you want this condition. And of course there's evaluation ring, which I'll write as V of nu, which is F and K such that nu of F is bigger than equal to 0. One has a convention here that nu of 0 is infinity. That makes this work out. And of course, the maximal ideal, this is depending upon what definition you want. It's either a local ring or a quasi-local ring, because it's generally not Noetherian. Okay, so this is notation. Now, what this allows you to do is have sort of embed or almost embed algebraic geometry in commutative algebra. So if you have a birational map between algebraic varieties, that means that they're isomorphic on an open set. Then what one can do is then you can make this more geometric by picking out evaluation, because if you fix evaluation, it determines a unique point on a variety. Okay, so given a big variety, a collection of local rings and evaluation, the valuation prescribes a unique point. This was Zariski's philosophy, and it was his discovery in which he built this machine all around. For a projective variety, there exists a unique point. And this is usually called Grothendieck's criterion for properness, which is the way it's taught in most books. Okay, so what we want to do is we have something which is singular, and we want to resolve the singularities. So what one wants to do then is to try to make it better, and this is by changing it birationally. So the way you do that is you blow up an ideal. So since we're using valuations that we can keep track of where we are by looking at the center of the valuation, the point which is dominated by the value, which is determined by the valuation, we blow something up to get a new variety, which hopefully is less singular, and then the valuation tells us a new point. Okay, so let's look at this this theory here. So let's take R to be an algebraic local ring, I an ideal in R, and nu a valuation of K. Such that R is contained in the valuation of nu, and the maximal ideal of the valuation ring intersection R is the maximal ideal of R. So one says that R is dominated by nu. Okay, now there exist F and I such that nu of F is the minimum of nu G such that G is in I. Okay, so we pick such a guy out. In fact, because the ideal is finitely generated, it's Noetherian, you can find this. Okay, so we construct this birational extension. We take I and we divide everything in I by F. So you can get this just by taking a set of generators and dividing them by this F. And then this guy sits inside the valuation ring. We localize at the pullback of I, of the maximal ideal. So this is a blow up along nu. That's how you blow up. And in fact, you can do this by, for instance, blowing up non-singular subvarieties, if you like. Okay, so one example of this is the normalization. Okay, so we have R into R bar. This is the normalization. Okay, and then we localize. That will be dominated by the valuation, since the valuation ring is integrally closed. Okay, so just taking the normalization and then localizing gives you this thing that we want. Okay, so this, now I can tell you about a problem of local uniformization. Yes?
Sir, can you just redefine, can you just show me the definition of the valuation of F?
Yeah, just a second. Where is it? This one right here, yeah.
No, so this is the definition of valuation, but I'm asking for the definition of F where you define the blow up.
Oh, okay, in the blow up. Okay, okay, so this R1 here is a uniquely determined local ring. It turns out that this is well defined, that if I pick any F which gives that minimum, the minimal value, and divide by it, I get the same ring.
Okay. So,
Okay. So this is
minimum of UG where G belongs to I. So what is the connection between F and G? I don't understand.
okay. This is the smallest value of an element of I. Okay, that's all that means. It's the smallest value of an element of I.
Okay, okay.
Everything in the field and thus in the ring has a value. Of course, if it's non-zero, I'm assuming here that I is a non-zero ideal. Okay, so, but basically this is just some construction that for the point of view of this talk, it's just you do some blow up and then you get a big ring, you get a new variety and this picks out a point on it. Okay, this is a problem of local uniformization. This is what Zariski called it. I guess it comes from the concept of uniformization of Riemann surfaces. And this is defined by Zariski. Given an algebraic local ring R and valuation nu dominating R, does there exist a blow up R to R1 along nu such that R1 is a regular local ring? Okay, so in fact, actually, if you do one blow up and then do another one, that's still a blow up. You can find some other ideal you blow up to get it. So this includes all sequences of blowing up. Okay, so this was the problem posed by Zariski, and in his paper, which appeared in 1944, he showed that local uniformization holds if K has characteristic 0. Okay, and using this, he was able to show at the same time, look, what did I do here? No, sorry. He was able to prove as a corollary of this which is that resolution of singularities is true for algebraic varieties of dimension less than or equal to 3 in characteristic 0. Okay, now this is a method which is this whole series. These theorems are filled with incredibly ingenious and beautiful ideas. That the method Zariski used to go from local uniformization to global resolution only works up through dimension 3, but that this method, Zariski's method actually uses characteristic 0, but it can be removed. And in fact, Abyankar did this as part of his proof of resolution in characteristic P in dimension 3. But the method doesn't extend, or at least no one's been able to figure out how to do it. It certainly doesn't easily extend to higher dimensions. Okay, so of course, the fundamental theorem of this is the final word in characteristic 0 is Hironaka's theorem, which was published in 1964, which tells us that resolution of singularities is true for algebraic varieties of arbitrary dimension over a field of characteristic 0. Okay, so this is the story in characteristic 0. In fact, Hironaka's proof is incredibly complicated, but he proves practically everything that's possible to prove in characteristic 0. So there's been some simplifications of the proof, many of them by Hironaka himself, and I guess now you can say a little more, but certainly the proofs have been made clearer since that time. But now, what about characteristic P bigger than 0, which was Abyankar's great interest? Okay, so first off, I should comment that even in the proof and resolution and singularities, the fundamental thing which makes it work is the existence of what Abyankar called the Chernhouse transformation, which some miracle happens when you do that, and locally everything becomes simple. It's just incredibly easy, although there's a tremendous amount of trouble about putting it all together at the end. But this observation or this discovery about you could, this Chernhouse transformation and its significance is in fact due to Abyankar. So in fact, he even played a big role in this proof of resolution in characteristic 0. Okay, so what about positive characteristic? Well, this is I'll tell you what Abyankar's fundamental work was on this, and the first paper was in 56. It appeared, and it continued on this. I think his last major work on this anyway was in 1966. Certainly that covers the results which I'm stating here. If either one of these cases, one, the dimension of R is equal to 2, and K has characteristic P bigger than 0. 2, the dimension of R is 3, and K has characteristic P bigger than 5. So the corollary to this is that by Abyankar is that resolution of singularities is true for algebraic varieties X if 1, the dimension of X is equal to 2, and of course, well, since it was known earlier in characteristic 0, maybe I'll say bigger and equal to. Okay, and the dimension, no, I think it works better for my next statement. I'll just leave it like that. Dimension of X is equal to 3, and characteristic K is bigger than 5. Okay, and I hope we have time to discuss a bit about where this restriction on the characteristic comes from. Okay, so this first, the surface case was in his thesis, and with Zariski, and this other one was later. In fact, this is really horrendous proof, and in fact, one summer I was in Trieste, and in the same place where Hironaka was staying, and every morning I would talk with him about resolution of singularities for a week, and this was just really an exciting week for me. What he explained to me was just how really important Abyankar's work was about this. And he got me very excited and motivated about this. And I went and I read his proof in Dimension 3, which is really an horrendous thing. You know, there's this long book on embedded resolution. And what one realizes after a bit of hard work, that's not the proof, that most of the proof is actually off somewhere else. So you come into this, you reach this point where you find this series of references to a number of other extremely difficult papers where actually most of the proof is. But anyway, this is a this is full of interesting and complicated calculations. Okay, so what's happened since then? What's the state of what is the state of the art of this? Well, there's a little more known, but surprisingly not very much. Okay, so there's a theorem by Kozar and Pilton in 2009, which says that resolution of singularities is true for algebraic varieties x of dimension 3 if characteristic k is bigger than or equal to 0. So this is an incredibly long paper also. It's two long papers, and it's I don't know, 200 or 300 pages long. That you see what they have done here is that they have gotten rid of this characteristic bigger than 5 assumption. They've also, in fact, they prove it for general excellent local ring, excellent schemes, which is the excellent reduced schemes, which is the best one can possibly hope for. Resolution fails outside of this. The definition of excellent actually appears in Abyankar's book on embedded resolution, where he proves definition 3. In fact, some years ago, I gave a talk once when I said something about an excellent local ring, and Professor Abyankar made some objection to this and was asking me about what was an excellent local ring and so on. And I told him to look in his book where it was defined. So, and he found that amusing. In fact, I always found that whenever I tried to have a little fun with him, he always responded very well, which I remember fondly. Okay, so this is that, but you see, it's kind of disappointing in a way that after all this work and time that we've just sort of improved things slightly. There's another theorem which in fact is of tremendous use in algebraic geometry, which is by de Jong, which appeared in 1996, which says that let X be an algebraic variety over a field K, then there exists an alteration phi from Y to X of X. So what is that? That is a finite extension a finite field extension L of the function field K of X and a blow up y of the normalization of x in L, which is non-singular. So the concept of normalization of x in L is was introduced by Zariski, although it's of course completely standard now.
In any characteristic?
Now, and sure, yeah, it doesn't matter. I mean, finally, if you want to be really fancy about this, you need something like a Nagata ring or something like, not Nagata scheme or something like that. But yeah, I mean, it works. Even Zariski's argument, well, he's got it, I think, even, yeah, I don't think when he did it, he had any assumption, but in any event, it doesn't require anything for it to work. For any algebraic variety over any field, it works.
All right, okay.
If
This
K is
dimension, can I ask a quick question? Dimension 3 result you mentioned, that does it use Abyankar's result for a higher characteristic, or it's independent proof?
It's well, actually, I'll say something now because I see at the rate I'm going, I'm not going to finish everything. I think I'm supposed to write something up, so I'll at least get everything in that. But yeah, in this result by Cozart and Pilton, actually, what they do is they use his methods, Abyankar's methods, to reduce to the case, and in fact, you need to use embedded resolution of singularities for surfaces, which actually Abyankar did prove. So if you use that, but his methods for from ramification theory evaluations, which he used and Abyankar used in his proof of resolution for surfaces, that those putting these things together, they reduce, just like Abyankar did for surfaces, they reduced to the case of an Artin-Schreier extension. And then they had some incredibly long involved proof of the Artin-Schreier extension. That even for surfaces, this was a hard case. But it's just out of this world for this Cozart and Pilton. And this is like a couple of 100 pages. And then, like Zariski and Abyankar, they finish up where I had mentioned that in dimension 3, once you've got the local uniformization, then you can prove global resolution. So that's what it is. So basically, what they've really done is they understood and used very well Abyankar's methods, and then in fact this Artin-Schreier case, which is the essential thing. But even then, there's an important invariant in it, which was really an invariant that he introduced for surfaces, which behaves pretty badly for surfaces. It's much worse for threefolds. And then after that, when you go into higher dimensions, it's just so bad one doesn't even know what to do with it, which is sort of why you're seeing this threshold of 3 here. Okay, so let me just a second. Okay, if K is perfect, let me jump back here. Then L is a separable extension of K. Okay, so this is de Jong's wonderful theorem that, we don't know how to resolve singularities, but after taking a finite extension, then one can get something which is non-singular. And this allows one to answer many questions in algebraic geometry, that you can almost pretend that you're, generally what it takes is something that would be sometimes there's a lot of work involved, but you can convert a theorem sometimes for, like for instance, you can convert a theorem which is true for a non-singular variety into a theory about a theorem about a variety which is not, or rather a theorem which requires resolution of singularities. Sometimes you can get around it, but not always. It's rather difficult. But anyway, this is somehow the best general statement. Okay. Okay, so now I'm going to mention one other problem, which in fact what's not so visible here is in fact that if you want to establish some kind of an induction, and say you know how to resolve singularities in dimension n, and you want to prove resolution of singularities in dimension n+1, you need a stronger concept, a stronger resolution theorem in dimension D. So the way, and this is the so-called embedded resolution. So if we take X to be a non-singular variety of dimension D+1, and Z codimension 1 subvariate of X, so that Z has a dimension D. So now locally, Z is the vanishing locus of a single equation. Okay, and this is Abyankar's proof of embedded resolution. To an characteristic P, well, all characteristics. Okay, so this is in fact in this in his proof of dimension 3 that he called the book where he finished it, I think it was called Embedded Resolution of Surfaces, something like that. And the reason why was because this was the significant part of the proof. This is where most of the work was. Okay, and this theorem is necessary for Abyankar's proof of resolution of singularities of threefolds. Okay, so now this is I think I'll have time to say a little more about this, but I think what I should at this point is say what is known and what is not known. As of this time, resolution is unknown in dimension bigger than or equal to 4, and embedded resolution is unknown in dimension bigger than or equal to 3. So I would say the next step if we use the methods which people are trying to use, who knows how one finally will settle this. The first step forward is to actually prove embedded resolution in dimension 3. So in fact, the thing which has really stopped us is we don't know how to prove embedded resolution in dimension 3, although we do know that there exists a resolution. And in fact, if this were true, that we would be able to prove local resolution of local uniformization at least in characteristic, bigger than 24. Okay, so let me say a little more. By the way, in case anybody noticed that didn't notice that in giving this talk, I'm attempting to put everything in the language in which Professor Abyankar himself saw things, and which I am very appreciative of myself. Okay, so I will say here, maybe I should share this, that when I first met Professor Abhyankar in 1988, when this was at Purdue, where my wife Hema and I were some kind of postdocs there, and we went to meet him, and I talked with him, and as a young person, naturally, I was a little nervous about talking with such a great man, but what I had, fortunately, my advisor Matsusaka had introduced me to the work of Zariski, and I'd read a lot of his papers very carefully, or as carefully as I could. So when I talked with him, I would always stick to the language which I'd learned from these papers. So somehow we established a good rapport right away, because I understood the language which he was working with. Okay, so let's talk a little bit more. Let me talk a little bit more about some of Abhyankar's work. While he's a PhD student, Zariski suggested that Abyankar try to extend the method of Jung to prove resolution of singularities in positive characteristic. Okay, and anybody I think who knew him has heard the story. This was something about these times that that this was, of course, a wonderful time in his life, and Abyankar was absolutely focused on this problem. Apparently, he would basically stay up all night working on this every night. So the his first result was what's called the Abyankar-Jung theorem now, and this was by Abyankar in 1956, and proven by Jung, the German mathematician Jung, for complex analytic surfaces in 1887, for maybe I should say germs of. Okay, and in fact, whenever people talk about this theorem, what they ascribe to him is actually much weaker than what he actually proved. So, which I will state here. So let's let R to S be finite, where R is an algebraic local ring, and S is normal. Suppose that the discriminant of R is a monomial in some regular system of parameters x1, xd of R. Further, suppose that if I take R, I localize at the ideal generated by xi, that's a height 1 prime, to S. I left something out here that's pretty, where R is a regular. Okay, assume that R xi to xi is tamely ramified for all I. Then the completion S hat, this is going to have this form. It's a power series in monomials in x1, 1 to the d, xd, 1 to the d. Okay, so the, did I leave something else out here? Yes, it's tamely ramified. Okay, so this is the essential assumption which makes this work. Okay, so where people usually refer to this is that in characteristic 0, all extensions are tamely ramified. And Abyankar in his paper on this gives examples of wildly ramified extensions where the theorem fails. Okay, so this was, I guess, his first paper, which appeared in 56.
Excuse me.
Okay, so I can tell you about what the method in characteristic of resolution in characteristic 0 is, which uses this theorem. This is a very beautiful proof where Jung's method to show that in characteristic 0, local, see, we have this assumption here, local embedded resolution of curves, which of course this is quite, oh no, sorry. Local resolution of local embedded resolution in dimension d minus 1. This implies local resolution in dimension d. Okay, so this is the important method. So if you're in a surface, this goes, the local embedded resolution is just embedded, just resolution of curved singularities. Okay, so let's let x be a d-dimensional characteristic 0 algebraic variety. I'll explain the method. What does one do? One's locally, you project x by a finite map onto a non-singular variety y of the same dimension d. the discriminant delta, that shows where the ramification is, has dimension d minus 1. This is the so-called purity of branch locus, which was proven by Zariski, Nagata, and Abyankar. Sorry, Auslander. Zariski, Auslander, and Nagata. By embedded in dimension d minus 1, we have a blow up phi from z to y such that z is non-singular. And the pullback of the discriminant has a simple normal crossing. Since I'm almost out of time, I won't explain what that is, that they're as close to being as non-singular as possible. Okay, let W be the normalization of Z in the function field K of X. The discriminant of W to Z is the pullback of delta, so by the Abyankar-Jung theorem, we have very simple singularities which can be resolved by a simple combinatorial algorithm. Okay, so this is kind of the ideal proof, and this is what Abyankar set out to prove in dimension 2, and as we see, he was able to make the critical part, this business about the this Abyankar-Jung theorem work in characteristic 0 and up to a point work in characteristic P. Okay, so in his thesis and published in '56, that what he did was he used a very clever, made a very clever use of the theory of ramification evaluations, which was mostly worked out by Krull. It's really a remarkable theory. And what it does is it allowed him to reduce to the case of an Artin-Schreier extension. So all he had to do was to try to make this one work. And in fact, this one, he makes a long technical argument. Well, compared to later things, maybe it's not that bad, but it's a pretty difficult argument. It's a very ingenious one, which allowed him to prove local uniformization for Artin-Schreier, a degree P extension, and then this other machine, the machinery evaluation theory, which he ingeniously applied, allowed him to prove local uniformization for any valuation on any surface, and then using this, he was able to use Zariski's argument to globalize this to prove resolution for surfaces. So I will stop here. I have some more things to say, but I'd like say a few things about his proof in dimension 3, which I didn't have time to get to, but when I write something up, I'll put that in it. Okay, so thank you. Thank you for listening to me. It was I was very happy to be able to be here to honor our master Professor Abhyankar.
Can I ask a question?
Certainly. Oh, I should
Hello?
have said this at the beginning, that because of the way I had to set things up, I can't really see chat. So, so people have to ask like you're doing.
Can you say
Yes,
a little
please, go
bit
ahead.
about the? Can you say a little bit about Bogomolov-Panteo's resolution of singularity?
Yes, it's the similar kind of idea, I believe, to actually what de Jong did, but it's in characteristic zero. It's been many years since I've looked at this, but as if I recall correctly, they also use this business about the irreducibility of the moduli space. Is that right? Anyway, it's been a long time. But I mean, I guess I guess that's sort of the other approach to this, which has been effective, which at least up to a point, which is this de Jong method, which that one I'm more familiar with his proof. And in characteristic zero, you can extend that type of method to get a resolution of singularities. And I believe Abramovich and someone else, maybe Karu, worked this out, where basically you can do it in such a way so that the finite field extensions are actually Galois extensions. So what you're really looking at is your quotient singularities. And in characteristic zero, quotient singularities are very simple and well understood. You can resolve them combinatorially. But in characteristic P, even when you can reduce to a Galois extension, that it's still not really understood what the what quotient singularities are. I guess Hoxter proved they were Cohen-Macaulay, but I don't think we know much else about them. But that's another approach which one could use for trying to prove this. Okay. So in fact, I believe. Yeah, as another comment that many years ago, everybody took it as sort of an axiom that, oh, of course, this thing is true, resolution of singularities in all dimension. But in recent years, I've heard amongst the experts a bit more caution, and also in some cases questioning whether or not it might not be true. And one approach to this, which Kozar mentioned to me, was that perhaps one can find a just this problem, that you can find a characteristic P quotient singularity which cannot be resolved.
Okay, thanks.
Yes, certainly. I mean, actually, just to interject something, if this thing is true, this resolution problem, and it's solved, I think there's a pretty good chance it's going to involve some just really new idea, a new direction. That it may be working, continuing with the existing ideas will get somewhere, but it just seems like we're getting into higher and higher level of complexity to do less and less. So there must it's maybe very hard to do anything unless somebody realizes that there's some wholly different way of looking at things, which makes it all come together.
Okay, so we thank Professor Cutcosky for a very interesting talk, especially related to the PhD work of Professor Abhyankar, and then what happens after that, and recent developments about it. So thank you very much, Professor Cutcosky. And
yeah, thank you. You're very welcome.
Yes, and now we request Professor Abhyankar, that is Shreedhar Abhyankar, who is brother of Shreeram Abhyankar, and he would like to give some comments. So I'm now requesting Professor Shreedhar Abhyankar. I hope he is here.
No. Yes, sir.
Yes.
Is
so
it
if you
audible?
want to give any comments, please proceed with that.
Yeah. Is it audible? Hello?
Yes, yes, certainly
Okay, sir.
audible. Yes,
So, yes,
it is
so
audible. Yes,
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 so my
yes.
father is going to speak now. Okay, yes.
Respected members of the organization committee and learned speakers and all those who are present today, that is on 22nd July 2021 for the online 91st birthday of the, the land for the online 91st birthday celebration 22nd July 2021 for the on the 20th birthday for Shreeram Abhyankar, the world famous mathematician. I am thankful to the organization committee for giving me a chance to speak on this occasion. I am Professor Shreedhar Abhyankar, younger brother of Professor Shreeram Abhyankar. My age is 89. I used to teach mathematical physics for MSc classes at Holkar Science College, Indore. During this, Professor Shreeram sent me books, Classical Mechanics by Goldstein and Mathematical Physics and Chemistry by Morgano and Murphy. Our father, Professor S.K. Abhyankar, was renowned professor of mathematics in college at Ujjain and Gwalior. He wrote a book on algebra in year 28-29 at Ujjain. And Professor Shreeram was born on 22nd July 1930 at Ujjain. So it can be said that he inherited the algebra since his birth. My father was Professor Shreeram's first guru. They used to sit together for hours together and study mathematics. Professor Shreeram used to state his father taught him algebra, and then in 1951 he proceeded to Harvard for advanced study and research. There he worked under the famous professor Oscar Dharisky. He was Shreeram's second guru. He taught him algebraic geometry, resolving this difficult problem of resolution of singularity. My mother used to say that Shreeram was a singular child, so he proved it later to be true. I will say there is advaita between Shreeram and algebra. Now I will state some interesting stories about Shreeram to demonstrate the preparation of hydrogen gas. He took a empty ink bottle, put some H2SO4 acid and a copper coin in it. There was a hole in the lid at the bottom. Shreeram fired a matchstick near the hole, and lo behold, what happened? The Shreeram, what happened? A blast was there, and bottle went flying, and on the hit on the roof of the. Thank God, nobody was there. Myself and my younger brother Srinivas, you used to say that we have played hockey and we will play cricket. To this, Shreeram used to reply that he played algebra and now he played geometry. At Gwalior, a very hot city, he would sit in sunshine and do mathematics. Then my younger sister Pushpa used to remind him, but about this, his reply was, "Oh, it is not very hot, son," showing that how he was so engrossed in uh, studying the mathematics. He used to say the pencil should be kept under the carpet, and one should want to study mathematics, he can take the pencil out and do mathematics. When he was in 4th or 5th standard, his study of mathematics was for some standard 11th and 12th. When he was in 11th and 12th, his study for MSc classes was complete. He used to quote a list of famous mathematicians, and then he used to attach his name last on the list. Then see how wonderfully he proved it. His mathematics friends have long list: Newton, Jacobi, Dardan, Dedekind, Riemann, Abel, Galois, Sylvester, Sare, Zariski, Abyankar, Nagata, Igusa, Hironaka, John Nash. John Nash used to take meal with him. Hironaka, and so on. I was fortunate to be present in 1990, the 60th birthday, Purdue. My son Yogendra was present to talk in 70th birthday. Myself gave a talk in 2000 in Purdue, and my wife Kusum sing a song. In the 80th birthday, 2010, July, Cutcosky are present. They are present here also. 12 July on Shreeram's birthday. And in 2010, this 80th birthday was in India at Pune. I was also present and gave a talk. In 220, on the 90th birthday, I gave a online talk just like this year, and July 2021. And taking all, thanking for all for patiently hearing me. Your affectionate Prof. S.S. Abhyankar.
Thank you very much.
Taking a small, yes, thank you. This is a small, going back to the memory of young Professor Shreeram Uncle and Hari Kashi and Aunt Yvonne Usha. This is just a picture.
Thank you.
Thank you very much.
Thank you very much. Yes, right. So thank you very much, Professor Shreedhar Abhyankar, for all these stories about Professor Abhyankar, Shreeram Abhyankar. Thank you very much. And now we will proceed to the talk of Professor Avinash Sathe, and many people are